St. Joseph College for Women, Autonomous, Vishakhapatnam. Welcome to St. Joseph Open Web-based learning platform, So E-Learn, for a soulful and enriching e-learning experience. Department of Chemistry presents St. Joseph's massive open online course, Solid States. Physical Chemistry, Module 3, Chapter Solid States, presented by Dr. B. Madhavi, MSc, MPhil, PhD, Department of Chemistry, St. Joseph's College for Women, Autonomous, Vishakhapatnam. Learning outcomes. Classification of solids based on binding forces as molecular, ionic, metallic, and covalent solids, able to differentiate between crystalline and amorphous solids based on long-ranged order, melting points, and physical properties. Understand and explain unit cells and their types. Simple cubic, body-centered cubic, and face-centered cubic. Explain the coordination number and its significance in determining the geometry of crystalline solids. Understand the concept of imperfection or defects in solids. Contents 3.1 Introduction, 3.2 Differences and properties of crystalline and amorphous solids, 3.3 Lattice point, unit cell and crystal lattice, 3.4 Symmetry in a crystal. 3.1 Introduction. We are aware that matter generally exists in three states, namely solids, liquids, and gases. When we alter the physical conditions such as pressure and temperature of the surroundings, we observe the states to change and transfer from one form to another. Solid state is a state of matter in addition to the liquids and gaseous state. In case of solids, the intermolecular forces are powerful and the empty spaces between the atoms, ions, molecules are very small. That is why they have a fixed shape and volume as well as high rigidity. Properties of solids. Solids have definite shape, volume, and they cannot be compressed or filled into a container like gases. Solids diffuse slowly and have high density. Crystallography. Crystallography is a science of crystal which deals with the study of crystal development and growth, their external form, internal structure, and physical properties. Crystalline substances are widespread. The majority of the objects surrounded us have a crystalline structure. 3.2 Difference between crystalline and amorphous solids basing on their properties. Shape. The crystalline solids have long-ranged order, that means the arrangement is regular. Amorphous solids have short-range order. The arrangement of particles is not regular or uniform. Melting point. Crystalline solids have sharp and definite melting point. Example, NaCl is having 801 degrees Celsius. Amorphous solids do not have definite melting point. Heat of fusion. Crystalline solids have definite heat of fusion. That means they have the ability to convert from solid to liquid. Amorphous solids do not have definite heat of fusion. Compressibility. Crystalline solids are rigid and incompressible. Amorphous solids are compressed to some extent. Cooling with sharp-edged tool. Crystalline solids breaks up into smaller crystals of the same geometrical shape. The broken pieces are not generally flat but have irregular surface in amorphous solids. Symmetry. Crystalline solids possess symmetry such as plane of symmetry, center of symmetry, and axis of symmetry. Amorphous solids do not possess symmetry. Volume. Crystalline solids have sudden change in volume when they are melted. Amorphous solids do not have sudden change in volume when they are melted. Interfacial angle. Crystalline solids possess interfacial angle. Amorphous solids do not possess interfacial angle. Nature. The crystalline solids are anisotropic in nature. They have different physical properties in different direction. Amorphous solids are isotropic in nature. They have same physical property in different direction. The examples of crystalline solids are NaCl, quartz, diamond, sodium nitrate, sugar, snowflakes, calcium fluoride, SiO2, alum, etc. The examples of amorphous solids are silicon, plastic, glass, rubber, polymer, gel, fused silica, thin film lubricants, etc. 3.3 Lattice point, unit cell and crystal lattice. A lattice point. In a crystal, each atom, ion and molecule is represented by a single point. A lattice point is a point at the intersection of two or more grid lines in a regular spaced array of points, which is also called as point lattice. Unit cell. Unit cell is the smallest repeating unit of the crystal lattice. It is a building block of the crystal. Crystal lattice. The three-dimensional arrangement of atoms, molecules or ions inside a crystal is called as crystal lattice or space lattice. The crystal lattice is made up of numerous unit cells. In the above example, the bricks are considered as lattice point, room is considered as unit cell, and building is considered as a crystal lattice. Types of unit cells. Unit cells are divided into two types, primitive unit cell and non-primitive unit cell. Primitive unit cell. The particles are present at corners. Example, simple cubic crystal. Non-primitive unit cell. Particles are present at corners and other position. Example, body-centered, face-centered and edge-centered. In body-centered, the particles are present at corners and at body centers. In face center, the particles are present at corners and face centers. In edge center, the particles are present at corners and edge centers. Contribution of an atom inside a unit cell. This means that how much part of an atom is present inside a unit cell. To know this concept, two examples are illustrated. Let us assume a ball is immersed in a vessel. About 50% of the ball is present inside the vessel and 50% of the ball is present outside the vessel. This 50% is called as contribution of the ball that is present inside the vessel or outside the vessel, or we can call 1 by 2 is the contribution of the ball that is present inside the vessel or outside the vessel. The second example is given by a gift was purchased by three persons, namely X, Y, Z for $8 and X spent $1 to purchase the gift. Therefore, the contribution of X is 1 by 8 out of $8. The various parts of the unit cells are face-centered, edge-centered, body-centered and corners. There are 8 corners that are represented by blue balls, 12 edges, 6 faces and 1 body center. The number of atoms that are present in body centered are 1. In simple center, 8 atoms are present, edge centered, 12 atoms are present and in face centered, 6 atoms are present. The contribution of body centered is 1 and the contribution of simple centered is 1 by 8. The contribution of edge centered is 1 by 4. The number of atoms are divided by 12 into 3, which is equals to 1 by 4. Therefore, there are 1 by 4 is the contribution of edge centered. In face centered, the contribution is 1 by 2. That means it has been divided by 6 number of atoms were divided by 3, which is equals to 1 by 2 is the contribution of face centered. In a cubic center, in a simple cubic cell, The number of atoms that are present in simple cubic cell are 8 atoms are present in corners and the contribution is 1 by 8, which is equals to 1. The number of atoms that are present in simple cubic cell are 1. In a body-centered cubic cell, there are 8 atoms that are present in corner and its contribution is 1 by 8. Therefore, number of atoms that are present in corner are 1. And in body-centered, the number of atoms present are 1 and its contribution is 1 divided by 1, which is equals to 1. The number of atoms that are present in body-centered cubic cell are 1 plus 1. Therefore, 2 atoms are present. In face-centered cubic cell, corner atoms are 8 and its contribution is 1 by 8. Therefore, 1 is the number of atoms that are present in corner. The number of faces are 6. Its contribution is 1 by 2. The number of atoms that are present in faces are 3. Total atoms that are present in face-centered are 4. In edge-centered cubic cell, the corner atoms are 8 and its contribution is 1 by 8. Therefore, 1 atom is present in the corner and edge-centered atoms are 12 and its contribution is 1 by 4. Total 3 atoms are present on the edge. Total atoms are 4 atoms. 7 crystal systems basing on edge length or axial distance and interfacial angle. Axial distance refers to the length of the unit cell edges along the 3 crystallographic axes that are given by small a, b and c. It represents the distance between two parallel planes of atoms along each other. Axial distances are important in describing the dimensions of the unit cell, which is the smallest repeating unit of the crystal. Interfacial angles are the angles formed between adjacent crystal faces. These angles are determined by the internal arrangement of atoms and are characteristic of each crystal type. They are usually represented by alpha, beta and gamma. Alpha lies between B and C axis, beta lies between A and C, and gamma lies between A and B. In a cubic system, axial distance is equals to A equals to B equals to C, and interfacial angles are alpha is equals to beta is equals to gamma, and all are equals to 90 degrees. All sides and angles are equal and they are highly symmetric. In a tetragonal system, axial distances are equals to A equals to B and B is not equals to C. Interfacial angles alpha is equals to beta and beta is equals to gamma, which is equals to 90 degrees. Two sides are equal and the third side is different. All angles remains 90 degrees. Orthorhombic system. Axial distances. A is not equals to B and B is not equals to C. Interfacial angles are alpha is equals to beta and beta is equals to gamma, which are equals to 90 degrees. All sides are unequal but angles are equal. Fourth one, monoclinic system. Axial distances are A is not equals to B is not equals to C. Interfacial angles alpha is equals to gamma, which is equals to 90 degrees, and beta is not equals to 90 degrees. All sides are unequal. Only one angle, that is beta, is not 90 degrees. Fifth one, triclinic system. Axial distances. A is not equals to B and B is not equals to C. Interfacial angles. Alpha is not equals to beta and beta is not equals to gamma, which are not equals to 90 degrees. No sides or angles are equal and all are symmetric. Hexagonal system. Axial distances are A is equals to B and B is not equals to C. Interfacial angles are alpha is equals to beta, which is equals to 90 degrees, and gamma is equals to 120 degrees. Two equal sides, one different, including 120 degrees angle. Seventh one, rhombohedral or trigonal system. The axial distances are A is equals to B is equals to C. Interfacial angles are alpha is equals to beta is equals to gamma equals to 90 degrees. All sides are equal. All angles are equal but not 90 degrees. 3.4 Law of crystallography. Three laws are given. First law, law of symmetry or symmetry in crystal, law of constancy of interfacial angle, law of rational indices. Crystals have inherent symmetry. The definite order arrangement of the faces and edges of a crystal is known as crystal symmetry. It is a powerful tool for the study of internal structure of crystals. Crystals possess different symmetries or symmetry elements. There are three types of symmetries: plane of symmetry, axis of symmetry, and center of symmetry. Plane of symmetry. It is an imaginary plane that passes through the center of crystal and divides it into two equal portions, which are exactly the mirror images of each other. Plane of symmetries are 9 types, in which 3 are straight and 6 are diagonal. Plane, vertical plane. Plane includes the principal axis and another axis. Second one, horizontal plane. This plane divides the object horizontally. Third one, diagonal or dihedral plane. This consists of principal axis and bisects the angle between C2 axis. Fourth one, axial plane. A mirror plane that lies parallel to one of the crystal axes. Fifth one, basal plane. This plane lies to the base of the crystal of a unit cell. Sixth one, diagonal plane. This cuts diagonally across the structure. Seventh one, symmetry plane that passes through the face. Where the eighth one, symmetry plane passing through an edge. Ninth one, symmetry plane that passes through vertex. Axis of symmetry. The axis of symmetry in a crystal refers to an imaginary line through the crystal around which the crystal can be rotated a certain number of degrees and appears to be the same as before rotation. Depending upon the degrees of symmetry, a crystal can maybe occupy the same position twice, thrice, four, or 6 times in a complete rotation. This is an axis passing through the crystal such that if the crystal is rotated around it through some angle, the crystal remains invariant. The axis is called n-fold axis if the angle is rotated to 360 divided by n. The equivalent configuration occurs after rotation of 180 degrees, 120 degrees and 90 degrees. The axes of rotation are known as two-fold, three-fold and four-fold axis of symmetry respectively. The rotation angle for the one-fold is 360 degrees, for two-fold is 180 degrees, three-fold is 120 degrees, four-fold is 90 degrees, six-fold is 60 degrees. Examples in common crystal. Cubic crystals like NaCl exhibits four-fold axis. Hexagonal crystals like quartz exhibits six-fold axis. Tetragonal crystals have a four-fold vertical axis. Center of symmetry. It is an imaginary point in the crystal that any line drawn through it intersects the surface of the crystal at equal distances on either side. It is a point such that any line drawn through it will meet the surface of the crystal at equal distances on either side. Since center lies at equal distances from various symmetrical positions, it is also known as center of inversion. It is equivalent to reflection through a point. Symmetry elements of cube. Center of symmetry are 1. Plane of symmetry are 9, in which straight planes are 3, diagonal planes are 6. Dyad axes are 6, triad axes are 4, tetrad axes are 3. Total number of symmetry elements are 23. Thank you for listening to my presentation.